Okay, so good day to all present. I'm Sanidhya Vijayvargiya, a student at BITS Pilani, Hyderabad campus, India. The title of our paper is Software Functional Requirements Classification Using Deep Learning with Various Hidden Layers. My co-authors for this paper are Dr. Kumar, Professor Lalita Bhanu, and Professor Sanjay Misra. This here is an overview of the various sections of the paper which I'll be covering in this presentation. I will cover the introduction to the topic and why this work is needed. We will look at the study design used in the study, as well as the empirical research framework. Then we will look at the experimental results, where we will see the visual representation of the results using box plots and analyze the results statistically using Friedman testing. Finally, we will look at how this work can benefit future researchers. So software requirements classification deals with segregating the client's requirements and demands found in the software requirements specification document into functional and non-functional requirements. It is a key step in the software development pipeline, which can be automated using machine learning techniques. Now, this allows the industry to save on labor expenses, and often a domain expert is required to do it manually, while also optimizing, and it also optimizes the process and saves crucial time. Now, functional requirements are the demands that the end user specifies as essential features that the system should provide. These are described as operations to be conducted, input to be delivered to the system, and expected output. Non-functional quality requirements are basic quality criteria that the system must meet. Now, these include portability, security, maintainability, reliability, etc. A key problem that needs to be addressed during requirements classification is that of the inconsistency in terminology that's used by the clients and the terminology that's used by the software engineers. And this can often lead to misclassification of the software requirements. The goal of this research is to provide a reliable and highly accurate deep learning model, which can be deployed in the industry to classify the software requirements. To accomplish this, we provide an extensive comparison of various word embedding techniques for the purpose of feature extraction, and we analyze which technique is best suited for the software requirement specification document. We also look at the effects of feature selection and dimensionality reduction on the performance of models. And finally, we look at how 8 different deep learning classifiers perform on the chosen data set to see which is the optimal classifier for classification purposes. Since the dataset chosen contains an imbalance in classes, the oversampling techniques have also been used to provide better results. Some of the technical challenges that are faced in software requirements classification revolve around choosing the right word embedding technique. Now, word embeddings help capture the information within the SRS document, and we get a numerical representation that is used as features for the rest of the machine learning pipeline. Thus, choosing the correct representation of the requirements is very important, and it's really crucial to capture the semantics of the text. A major problem that has been faced in previous research is that of the imbalance in the data sets used for training software requirements classification models. This is also something we address. Now, the dataset used to validate our models is the PROMIS dataset, which contains 625 labeled requirements taken from a group of 15 projects. The PROMIS data repository is unbalanced in terms of functional and non-functional requirements, with 382 out of 625 being quality requirements or non-functional requirements. Thielen Huang, with the help of his team, extracted the data and rendered it for public use. So here we can see the various word embedding techniques we have used in this work. First, we have continuous bag of words, skipgram, word to vector, glove, and finally TF-IDF. A point to note is that some of these word embedding techniques, such as TF-IDF, which is used here, are not able to capture the semantic information present in the text. For feature selection, we've used rank-sum test. When the data consists of independent samples from 2 populations, the rank-sum test can be used to test the null hypothesis that their distributions are identical. When the value of the test statistic is either considerably large or significantly small, the rank-sum test is used to reject the null hypothesis. And we've also used dimensionality reduction with principal component analysis. And it basically reduces the dimensionality of the data set, and it improves interpretability, and and also minimizes the data loss. And to obtain the lower dimensional data, we merely select like the top principal components. And while some information is lost, we're sacrificing the accuracy for simplicity. And when the features are highly correlated or redundant, uh, dimensionality reduction techniques can help improve performance of models. For the classification, we've seen that deep learning methods are gaining popularity in producing the best performance compared to other classifiers. And we use these methods to try to find the best architecture for the problem. And so basically, we've we've taken the promise data set, and we've divided into training and testing subsets, and categorized it using 8 deep learning models using K4 cross validation with the K value of 5. And all models have an input layer with the number of neurons in the input layer equal to the number of features of the input data. And for each subsequent hidden layer, the number of neurons have been halved. And then all layers involved in the deep learning models are either dense layers or dropout layers. And in this work, we've used a dropout value of 0.2 for the dropout layers. And finally, the output layer consists of only one neuron, which contains a binary value corresponding to a binary classification. Now, since we've taken this data set and split it into functional and non-functional requirement data sets, and so what we do for each of these data sets is either classify a requirement as functional or non-functional, or is it functional or not, or if it's non-functional or not. And the activation function for each layer is the rectified linear activation function, or ReLU, and except the output layer, which uses a sigmoid activation function. And for the loss function, we've used binary cross entropy with Adam as the optimizer. Now, here is the most simplistic model, or like our first deep learning one, DL model 1, as in the paper. And this is the most simplistic out of the 8 models used. And as you can see, the input and output layers are dense layers. And in the other models, the depth of the network varies, and we basically increase the number of layers. And between dense layers, we add dropout layers. And these dropout layers are used to basically help solve the problem of overfitting. And similarly, we are increasing the number of hidden layers for more of these deep learning models. So here we have the like the initial promise data set, and we basically apply the watermelon techniques, and then we apply the oversampling technique, the smooth oversampling technique, and then we apply the feature selection technique in the form of rank sum test and the principal component analysis for dimensionality reduction. And we also preserve the original set of features, and then we compare the performance of these two dimensionality reduction and feature selection techniques, and see how the performance of the models changes with each of these sets of features. And then finally, we use the 8 deep learning classifiers and then we perform analysis based on the results. And to evaluate the models, we've used 4 metrics: accuracy, precision, recall, and area under ROC curve. Now, these are the performance metrics, and here we've only shown accuracy and AUC values. Judging by the AUC values, you can see they're pretty high, and the lowest one is around 0.74, or greater than 0.7, which shows a reasonably good performance. And here you have like these are for the original data set, and these are after the application of the oversampling technique, synthetic minority oversampling technique, SMOT. And so now we'll be using box plots to visualize the performance of the different techniques we've used. And so coming to the word embedding techniques, here we can see that the TF-IDF technique has performed better compared to the others, and it's resulted in reasonably high AUC values. And we verify these results using statistical testing in the form of Friedman test. And here the p-value used is 0.05. Basically, we compare these mean ranks, and the lower the mean rank for a specific word embedding technique, better is the performance. So as we can see, TF-IDF has the lowest mean rank. That means it had the best performance, and word-to-vector has proven to be to do reasonably similar as well. Next, coming to the feature selection techniques, and then here you can see that rank sum test is marginally outperforming the original set of features, and principal component analysis has not done so well in comparison. Now we can verify these results using the Friedman test. And here again, we see that the rank sum test has the lowest mean rank. And again, the p-value used is 0.05. But also what we notice is that principal component analysis or dimensionality reduction techniques have basically regressed the model. And instead of those, using the original set of features is more beneficial. And obviously, the best performance has been observed with the feature selection technique or rank sum test. Now we look at the classification techniques. These are the eight different deep learning models. And it's hard to tell which ones did the best using the box plot diagrams. This we can analyze better using the Friedman test mean ranks. And here again, we see that the deep learning 3 model has the lowest mean rank. And basically like the model we saw, the simplest model, has the highest mean rank that shows it has the worst performance out of the models we've compared. Now the deep learning 3 model, it basically consisted of a dense input layer followed by 3 more dense layers. So that was the structure for the deep learning 3 model, which had the best performance. And this is a comparison of how the performance improved with oversampling. And it's clear to see that it has a positive effect on the performance of models. And there's a considerable improvement. And this is validated by the Friedman test. As we can see, the 1.23 is the lowest mean rank out of the two. And again, the p-value used is 0.05. So finally, coming to the conclusions. So the model that utilized features extracted from TF-IDF had considerably better performance. But since we also noticed that word-to-vector had similar performance, and it has considerably less number of features compared to TF-IDF. So maybe that can also be used instead to minimize the computational based on the requirements. And out of the 8 deep learning classifiers, deep learning model 3 had the best results, and deep learning 2 and deep learning 4 classifiers provided similar performances. And again, as we saw, the rank sum test features outperformed any other group of features. And oversampling had definitely shown to be a positive, and this mode-based oversampling is something we definitely recommend for future researchers. And as we saw with the performance tables, the AUC values were generally high, and so deep learning-based classifiers are certainly something that should be used for software requirements classification. These are some of the selected references. And any questions?
Great, thank you very much. And again, a very nice presentation, and thank you for keeping the time. Do we have any questions? I don't see any in the chat. Can I make one small comment?
Yeah, definitely.
Cleland Huang is a lady. It's Jane Cleland Huang. And I know this because she's attended SEW many, many times.
Okay, so sorry for this.
No worries, it's just a small thing. She's not here to get upset by it, but some people would be.
Yeah, definitely. I'll keep that in mind.
So is this very much your current research as a student? Is this for your thesis?
This is not for my thesis, but I'm working on under Professor Love Kumar for throughout for the last couple of last year or so.
Okay,
And this is the work I've done under him.
very good.
I actually do not have the 15 projects, exactly the information about that.
Okay. Maybe you could just make a generalization.
They were taken from the data was collected from public repositories, as far as I'm aware, and this data set has basically been used by in previous research as well. So we use this for basically benchmarking the values, and more than that, I'm not sure.
Okay, that's fine. So I mean, you basically used it so that you could compare to other experiments that have been done.
Yeah, that was the goal.
Very good.